We'll explore the validation of cryo-EM maps. So just a reminder where we are coming from. So we acquire data with the electron microscope and direct detectors, and the signal to noise ratio at the level of frame is in the order of 1 over 1,000, meaning that we have 1,000 times more noise than signal. When you average all those frames, but first you have to align them, which is not an easy task, then we are a bit better. We have a signal to noise ratio of 1 over 100, and we can barely see the particles in there. So here we have some protein of our interest, and then from this very noisy data we want to construct atomic models of our proteins. So in all these processes we will have to estimate parameters, and these parameters, when we estimate the parameter, that will be an underlying ideal parameter, which here it is shown with the reconstructed map, but it applies to all parameters, and we will have some perturbation around that ideal parameter. So that perturbation will be random, so we'll have some oscillations around the value, and this central value could be the ground truth. It can be something else. So if it is something else, then we say our parameter estimation is biased. So here we will have our reconstructed map, or in general our parameters will be the ground truth plus a perturbation that is random. So this random perturbation, the expected value of that random perturbation will be the bias, and those are systematic errors, while the variability is encoded by the covariance matrix of that parameter, or the variance of our parameter. So in general, we can say that, let's say that we have a fraction of parameters for which we have correctly estimated its value. So we are in this regime, even if we have some noise, but we are in this regime with no bias. Then this fraction p will result into a more or less correct structure. But the remaining of the parameters, these ones here, so 1 minus p, will give a completely incorrect structure. So our reconstructed map will be a mixture between the two. So this idea that we have incorrect estimations, how can we know? Because you estimate the same parameter several times with the same algorithm, or ideally with different algorithms, and then you can compare the different alternatives, and then you will recognize those for which they disagree quite a lot. This idea of putting everything in and the algorithm will know is clearly suboptimal. And the current situation is that sometimes we have maps reconstructed like this. The same data processed in a different way gives this map. It is not a particular criticism to these particular people and structure. It is a general warning that if you don't pay attention to the details underneath, you may end up with artifactual structures. And what I'm going to present was published in Faraday Discussions last year, and it is putting together all the image processing tools that are available for the validation of cryo-EM maps. And we propose a validation of the maps that is based on different levels. So the most basic level is just having the map, and now we have moved as a field, we have moved to level 1, where you are required the map and to have maps. But then many more levels could be possible. So you have also 2D classes on your path. You have particles, you have angular alignment, you have micrographs and coordinates. So you can give all these, and you can go up from level 0 to level 5. And on top of that, you can also give an atomic model. You can give the workflow that you have used and the results that you have obtained along the workflow. you can compare to other techniques. So let's see, and all this information can be put together into a report, a PDF report, and let's see how this report looks like. So let's say that you have only the map. So with only the map, there are already a number of things that you can check. So for instance, you can check whether the map is correctly centered. So correctly centered because you need extra space around the map, around the structure, in order to correct properly the CTF. So the CTF extends 30-40 angstroms around the structure, and if you don't have this extra information, you cannot properly correct for the CTF. You do an approximation, which is sometimes it is pretty good, but that depends on the defocus, but you don't have enough space. So you can also check whether the threshold that you have given gives a smoothly well-connected mask, or it scatters the mask into many small pieces. You can also analyze the background. All algorithms, 3D reconstruction algorithms, they assume that the background has zero mean. Is that true or not? Are there outliers? Yeah, there are many things, some of them related to local resolution, checking the hand, and the kind of report that we get is for every item in this list, we get whether the test passes or not. So for instance, in this particular example I was using in this report, the mass analysis and the mask analysis are fine. The background has a problem. So the problem is that the background doesn't have zero mean, and there is a significant proportion of outlier values. And now you can go to the map and check whether that is true, that is not true, whether you don't care about that, it doesn't matter, or it matters and then you want to process something. Also, for instance, here the reported resolution is particularly high with respect to the local resolution distribution, and then here we can see, so we have reported a resolution of 2.6 angstroms, while the local resolution distribution is more centered around 4, and 2.6 is in one of the extremes. So if you give the half maps, the typical approach that we have in the field is to calculate the Fourier shell correlation, which is fine. It is a global method, and as long as we all report the same the resolution with respect to the same threshold, that's fine. Remind always that the FSC compares two halves. So if you make systematic mistakes in both halves, then systematic mistakes are rewarded by the FSC. So you have to be careful with those numbers too. So you have a global resolution measured by the standard FSC, but you have also other ways of defining your threshold. For instance, this permutation test FSC, which I think has a very solid statistical background. Then you can also do local resolutions like block res, resmap, monores, directional resolutions, monodir, or also more directional or anisotropy measurements like FSO or FSC 3D. And then for each one of them you can check whether the map is passing the test or not, and if there is a warning. So for instance, here there were two warnings. One was ResMap, that was again complaining that the reported resolution was too high, and here you have the kind of report, a page from that report. So you have the distribution of local resolutions according to ResMap, you have a table with significant percentiles or important percentiles. Here you have an explanation, and then you have down you have the warning. And Monodir is complaining that the distribution of resolution in directions it is not uniform. then if you give 2D classes, then we can compare the 2D classes given by the user from the 2D classes computed from the map. So we can align those 2D classes to the map and reproject the map and check whether they correlate sufficiently or not. Then if you give particles, we can check whether there are outliers in those particles, so there are particles that are jumping all the time between in a 2D classification. We can also classify the given particles in 2D, compare the consistency of the classes computed from the particles to the classes provided by the user. And it doesn't mean that you have to give, if you have made your structure with 500,000 particles, you have to give the 500,000 particles. You can, but at least give a random subsampling of that, a random sample of that 500,000 particles. So maybe with 10,000 or 15,000 particles, it is enough. So also we can check the angular assignment. You have done your own angular assignment, again not for the 500,000 particles but for a random subset, and then we can check whether those angular assignment, so the reprojections of the map along those directions, they give the same they correlate well with the experimental data. We can check whether particles can be easily aligned. Those particles are easily aligned, and there are ways to define that. This alignability, smoothness, alignability, precision and accuracy. Then we can also make a state-of-the-art angular assignment, so we can rely on CryoSpark in these reports, but you can now use also XMIP or whatever, and we can check whether the newly assigned angles are similar to the ones that you have given. We can detect overfitting. We can check whether the angular distribution is sufficiently uniform. This is another way of measuring that. We can analyze the stability of the defocus parameters, for instance, and then we can give, for each one of these items, we can give whether the test is passing or not. And for instance, here we see that this particular set of particles, the number of particles whose angular assignment is significantly away from the smooth maximum is too high. So these are particles that are difficult to align. There are, according to CryoSpark, there are a percentage of images with uncertain shift. So more than 20% of the images have an uncertain shift. Or we can compare Reliant and CryoSpark or the CTF, or so here you have the kind of angular comparisons, and then you see this is the alignment, a comparison of the alignment between CryoSpark and the one of the user. So in angles they're fine, they agree, but in shifts they don't agree, and the same between Reliant and CryoSpark. Then if you gave us coordinates, we can use an algorithm that removes coordinates that are coming from, you have to give the coordinates a micrograph. So we remove those coordinates that are coming from aggregations, contaminations, carbon edges, all those stuff. And then we can check how many particles we have, how many coordinates we have removed. And if it is a significant amount, then we cannot trust those reconstructions so much. If you give an atomic model, there are many other tools that you can use. Here we try to be complementary to the checks of EMDB. So we implement MapQ, FSEQ. We can fit multiple models with molecular dynamics and see which parts are more variable. We can compute linear plots of the models and the map and compare them. We can use the Phoenix validation tools, EMRinger, DAG, and for each one of them we do the same. So whether the map and the model now pass the test or not, and if they don't pass the test, why. So here is some more example of the kind of results that you get. So for instance, you can check what is the cross correlation between the map and model for all the residues. You can do analyze that by chains. You have all kind of FSCs calculated. These ones are the ones given by Phoenix, and there are evaluations of P factors, and you can give your workflow. So you can give your workflow so that people can understand which were the logic and the data analysis pathway that you followed, and you can upload your workflow to a repository of workflows. You can make it public or not. Ideally, you would like to make it public so that people can understand your result. For the moment, it is only useful, or it can only be used with Cypion workflows, because we are the ones that better define or that are developing all this kind of stuff. And if you connect to that web page, what you can see is that in the PDF you see a summary of the workflow, but if in the web page you can also interact with the workflow. So you see all the workflow steps, and if you click on any one of them, you can see the parameters that you have used, a summary of what was the input, what was the output. We show a few images of the output so that you can figure out more or less the kind of data that you had there. It is we are showing just 3 images out of, let's say, 5,000 micrographs that you have, so we cannot show everything, but at least you get an idea of what was going on. And you can compare to other experimental techniques, so you can compare to mass spectroscopy, to SACS. You can do Tilper validation, and then for instance here it is a comparison of the SACS curve, experimental SACS curve, and the simulated SACS curve, and they should agree. And here you have some examples. So here are 3 maps of the SARS-CoV-2 spike protein, and they all claim kind of similar resolution, around between 3 and 4 angstroms, but you see that the maps and the quality of the maps are quite different. So first of all, and this we already know, this resolution is the best resolution of the map, so it doesn't mean that all the parts of the map will have the same resolution, but even that we see that the features of the map are quite different. So for instance, now with the information available, we can make a number of tests, and this one is passing 14 out of 20 tests, and this one they are given fewer information, and then it only passes, we can only check 13 tests, and it is passing around a half of them. This one is a little bit more than a half. So another example, this is one of the best structures that as a community we have produced. So this is an apoferritin at 1.15 angstroms resolution, and even this very good structure, it has many warnings. So let's see kind of warnings that we have. So for instance, the threshold doesn't seem to create a mask that is very well connected. The background is not zero mean, it has many outliers, the P factor is outside this interval, the MapQ, so different tools that compare the map and the model are complaining, and all this can be accessed through this web page. So if you connect to this page, you can submit your own map and all the data that you want to give, and then the report will be constructed for you. This report is in principle private, but you can make it public So the report, depending on the amount of information you give, the report can be quite complete. So you see that it can go up to more than 100 pages, and this is a very very thorough analysis of the quality of your map. And with this I'm done, and thank you all for listening to this, and I hope that you check your maps before submitting to EMDB.